literally hundreds of studies implicating this region as a mechanism for attaching meaning to words. As would be expected when viewing language as a network, temporal neuroimaging methods have shown that this semantic processing occurs milliseconds after phonological processing at earlier stages. As a general rule, as information travels further towards the anterior part of the temporal lobe, the neural mechanisms become increasingly specialized for processing more complex semantic information. Another notable feature of moving towards the anterior portion of the ventral stream is that it becomes increasingly more left lateralized. So as it gets specialized for complex semantics, the left hemisphere takes on more and more of the processing burden. However, we know from brain lesions and neuroimaging studies that the right hemisphere is still involved in processing meaning, but it does a much more coarse-grained analysis. For example, if you were to hear the word key, the left middle temporal lobe would associate the label with a relatively narrow meaning of key, an object that unlocks things, whereas the right hemisphere homologue makes much more distant connections, such as the metaphoric meaning of solving a problem. So how does the temporal lobe associate conceptual meaning to words? It's a matter of much debate, but one hypothesis is that the anterior temporal lobe is a neural hub that connects word forms to various meanings that are scattered all around the brain. By now, you should not be surprised that the semantic system for language involves activation of a very complex and widely distributed memory network. So what is this network composed of? One of the largest meta-analyses on the brain's semantic system for language, Jeffrey Binder and his team at the Medical College of Wisconsin reviewed over 500 PET and fMRI studies and found that there were a few main areas of activation. One area was located in the cortical area surrounding the left auditory cortex, including the left temporal lobe and parts of the inferior parietal lobe too. Connections to these areas are thought to activate visual imagery. To appreciate this, it's good to be reminded of simulation theory, which we talked about earlier. Recall that simulation theory explains that one way we remember things is to reactivate parts of the brain that are involved in actually perceiving them. So one mechanism for remembering the meaning of the word key is to reactivate the visual perception of images of keys. However, it's important to note that semantic memory and visual perception do not completely overlap. We know this because there are cases of brain damage to these visual areas where object recognition is completely lost, but patients can still correctly understand the meanings of words associated with those objects. So for example, a person may lose the ability to visually identify a key, but they could easily tell the difference between a house key and a car key. This means that concepts linked to language are not totally the same as images linked to perception. Another simulation zone is located in the motor and premotor cortex of the frontal lobe. If you recall from the work of Friedman Pulvermuller, when someone hears the word kick, the foot region of the primary motor cortex becomes active, but when they hear the word throw, the hand region gets involved. Again, the overlap is not perfect because there are cases of brain damage where the motor system is compromised, but linguistic knowledge about what objects do is perfectly fine, it's preserved. In addition to neocortex activation, limbic regions also get in on the act of attaching meaning to words. Not surprisingly, the part of the subcortex responsible for encoding and retrieving memories, the hippocampus, is constantly active when searching for word meanings. And because many words have episodic and emotional associations, parts of the cingulate cortex become active to attach those associated meanings. If you think Binder's brain network is impressive, consider this semantic atlas created by Jack Gallant and his team at Berkeley. In 2016, Gallant conducted a methodologically innovative study measuring the brain's semantic processing not of isolated words, but of whole narratives. He had 7 subjects come into the lab and listen to 2 hours of stories from the Moth Radio Hour, while he measured fMRI to activations of each word in the stories. And what he found has greatly expanded traditional views of the brain's semantic network. Gallant's team found that words activated practically every square inch of the brain's surface. Consistent with Binder, the activation maps were highly organized. Color words activated brain areas involved in color processing, and social words activated areas involved in social processing. And as with Binder's study, the same words activated multiple brain regions, suggesting that word meanings comprise a multimodal web of activations. Lastly, although the maps of each of the 7 people differed in the details, they all showed remarkable general similarities of brain locations. This suggests that different parts of the brain may be optimized for processing the meaning of language in similar ways across all humans. Okay, after the meaning of words is assembled from all corners of the brain, the information is channeled towards the final stop on the ventral pathway, the left inferior frontal gyrus, or IFG. We've talked about this brain region earlier, and you may recall that it's involved in the integration of multiple pieces of information. In this case, the information that must be integrated is the meaning of words and their syntactic context. This final step is necessary for comprehending language in its full creative complexity. Many fMRI and PET studies have shown that the left IFG is active when people process words as part of a syntactic frame. MEG and ERP studies have shown that the timing of this integration is variable. In the case of ambiguous syntactic sentences, it often occurs tenths of a second after the processing of word meanings. However, when the syntax of a sentence is very familiar, like the boys pet the dog, the left IFG actually becomes activated in advance of the word dog to predict word meanings that are associated with such a reliable syntactic frame. This illustrates an important property of the ventral stream of language. It can flow in both directions. To illustrate how the left IFG constantly keeps track of syntactic structures, Stanislas Dehaene and his team in France have measured a process called merge. The merge mechanism is theorized to monitor syntactic phrase structures in sentences. As in, and this is a real example, 10 sad students of Bill Gates should often sleep. According to the theory, the merge process builds up in the left IFG with each word in the first phrase, and then when the first phrase is complete, it resets itself with the start of the second phrase. In this way, merge is a mechanism for keeping track of syntactic structures in a language. Dehaene and his team measured merge in epilepsy patients who had neurostimulating electrodes implanted in their frontal and temporal lobes to control life-threatening seizures. Because those electrodes could record, in addition to stimulate, it was possible to get a rare inside peek into the neural mechanisms for syntactic parsing of a sentence. Just as predicted, the left IFG increased activity as the phrase structure built up, gradually progressed, and then released activity at the phrase boundary. This is some of the most direct evidence that the left IFG is constantly monitoring and updating the syntactic context of language, which is not only useful for correctly understanding complex meanings, but also for predicting meaning that is coming down the stream. As I mentioned earlier, these syntactic predictions can work backwards to help earlier phonological and semantic stages anticipate what phonemes and words to expect. Clearly, there's a lot going on in the ventral stream, but it's only half the story. While information moves up and down this pathway, a second set of processes is ongoing in the dorsal stream. If you think about words as objects, the function of the dorsal language stream is to act on those objects. This is not as much of a stretch as it seems. One way for the visual system to know an object is to interact with it. In a similar way, one way for the auditory system to know what a word is to produce it. So for the dorsal stream, knowing is doing. The significance of this knowing as doing mechanism is clearest when considering how infants learn to produce language in the first place. When a baby babbles, It's coordinating its motor system to match what its auditory system is hearing. Recall that humans are born with an ability to hear all phonemes, but the motor system is much less advanced. It requires months and months of practice to learn how to produce the phonemes it hears. This extensive experience is what lays the tracks for the dorsal route in the first few years of life. And once it's in place, we keep using it after we've mastered the speech sounds in our language. So let's trace out this pathway. The first stage of the dorsal route goes from Wernicke's area to the left Sylvian parietal temporal region, or SPT. Sorry for all the different SPTs and MRIs, that's just the way neuroscience is. SPT gets its name by straddling the Sylvian fissure, which divides the temporal lobes and the temporal and parietal lobes. As a general rule, the dorsal stream is much more left lateralized than the ventral stream. And this is because motor commands for producing speech are located mostly in the left hemisphere. Much more on this in the next lecture. The SPT takes the phonological signal from earlier stages and rehearses it. You can think of this as a neural replay device. We know this for a couple of reasons. One major piece of evidence comes from a unique speech disorder called conduction aphasia. Damage to the left SPT causes errors in the production of phonemes, despite the ability to distinguish them during language comprehension. So these patients could easily comprehend the phonetic and semantic distinction between pate and alate, but would have great trouble accurately distinguishing the words in their own speech. Another function of SPT is to learn new vocabulary items. Spatial neuroimaging shows that when adults hear a new word in their L1 or L2, in their native language or a second language, the SPT serves as a mechanism for subvocally rehearsing that word to commit it to long-term memory. Interestingly, this rehearsing happens mostly for complex words. For words composed of relatively simple or highly familiar phonemes, this stage seems to be skipped and is handled downstream towards the end point of the dorsal route. The main path for this downstream connection is a tract of white matter fibers called the arcuate fasciculus, which in Latin means curved bundle. The final stop of these fibers is the left prefrontal cortex and IFG. Now, we know that those regions are heavily involved in overt speech production. In fact, damage to the left IFG is what produces Broca's aphasia, which we'll talk about more in the next lecture. But Broca's area and the left IFG more generally also serve a syntactic function. It's long been observed that Broca's aphasics have deficits in comprehending complex syntactic sentences. The syntactic function of the left IFG has been corroborated in many functional imaging experiments. And developmental studies have shown that children's syntactic abilities are positively correlated